This is a lecture of some of the historical background and experiments that motivated the development of quantum mechanics. So going back to the end of the 19th century or the beginning of the 20th century, the so-called classical physics is well established. So that includes the three pillars: the classical mechanics, the classical electrodynamics, and the classical statistical thermodynamics or statistical mechanics. So these are three pillars of classical mechanics was able to explain almost everything people observed at that time. From the thing that run on the ground to the things that fly in the sky, and even the motions of planets and the stars. Was a big success. Okay, so what comes with this success is two major problems. One, the first one is all these theories, all these classical theories, from classical mechanics to electrodynamic and statistical mechanics, are deterministic. Meaning that so all these laws of physics are described by differential equations, which require initial conditions to solve. But if we can define the initial condition, like all the future behaviors are exact. So in a way, if you know at certain point of universe or at the beginning of the universe, then we should be able to predict everything that happens in the future using these classical laws. So this is success, but at the same time, it's a little bit scary. So that means everything in the universe, from the planets to even the lives on Earth, including us, are determined by this classical physics. So that means, in particular for us, whatever we do and whatever we say and whatever we think were determined long time ago at the beginning of the universe. So in that sense, we might be thinking, do we even have our so-called free will? So there were a lot of philosophical discussions at the end of the 19th century. So if the classical physics is everything, so that means we don't even determine what we think and what we do. So where is our free will? So what distinguishes us from like other objects, like a table, okay, or animal like a fish? So that problem, of course, didn't get solved at that time. Even nowadays, the discussions keep going. Especially lately, we're able to create very impressive AI. So that also makes us to wonder: do we even have free will? Okay. So this is one of the problems of classical physics. Everything is deterministic. So this problem is sort of mitigated when the quantum mechanics was discovered. So in quantum mechanics, it is intrinsically non-deterministic. So in that sense, maybe we can recover some of our free will in this uncertainty in quantum mechanics. Okay, so the second problem of this classical physics is that it can explain almost every phenomena, almost every experimental observations, except a few outliers. So there are a few experiments that cannot be explained by classical physics. Okay, one important example would be the behavior of subatomic particles. So experiments that cannot be explained by classical physics. So one of the topics we're going to cover in this class is the atomic and nuclear physics. So unfortunately, the subatomic particles such as neutrons, electrons, and protons do not follow the so-called classical physics. So that all these new experimental observations motivated us to develop a new physics, which is now known as the quantum mechanics. Okay. So in the next few minutes, I'm going to explain some of those experimental facts that can be used to motivate the study of quantum mechanics. So the first one is related to a stable atomic model. So after Rutherford did the Rutherford scattering experiment, then we know atoms are made of positively charged nucleus and negatively charged electrons. And the majority of the mass is concentrated in the nucleus. So if we roughly draw the structure of an atom, then we have positively charged nucleus. And then outside, we have the negatively charged electrons. Okay. So then the natural question is, how do the electrons move? So using classical physics, we can imagine electrons are moving around the nucleus in a circular fashion. Just like how the moon is circulating around the earth and how the earth is circulating around the sun. Okay. So, so far so good. But now if you think about this, so electrons have charge, the negative charges. And from the classical electrodynamics, or EM, electromagnetism, which is described by the Maxwell's equations, we know that every moving charge particle with acceleration, so charge with acceleration, is going to lead electromagnetic wave radiation, EM radiation. Okay. So just like when we moving current inside the antenna, then we can generate radio waves. Okay. So whenever we move charge with acceleration, then the charge is going to irradiate electromagnetic waves. Okay. So now we are moving. If the model of atom is like what I draw here, electrons going around the nucleus, then the motion of the electron is not on a straight line. So that leads to acceleration. So if the electron is going around the nucleus, then it's going to give out electromagnetic radiation. And of course, this radiation carries energy. Then the speed of the electron, because of the loss of energy due to this electromagnetic radiation, is going to decrease. So in this classical model, then the behavior electron is going to be not a stable circle, but in the end, the electrons going around the nucleus, and then give out electromagnetic waves and lose energy and eventually collapse to the nucleus. Okay. So electrons will collapse into the nucleus. Okay. And with the accrued estimation, which will be assigned in the homework, then you will see the lifetime of this electron is actually very short. Within a very short period of time, electrons is going to give out all of its energy, all of its potential energy and kinetic energy, and then collapse onto the nucleus. So we'll never be able to have a stable atomic model according to classical electrodynamics. So what accompanies with this radiation process is that the velocity of the electron continuously decrease to zero. Then the irradiated spectra of the electromagnetic wave should be continuous. So what does this mean? So this means if we indeed have to use a classical electrodynamics to describe the behavior of electron inside the atom, then those electrons will not stay there forever. So they will quickly collide with the nucleus. And during this process, the electron is going to irradiate electromagnetic waves. And those waves should be continuous. Okay. And obviously, that is not what we see from our daily life. So atoms are very stable. So we don't really see electrons colliding with the nucleus on a daily basis. Right? So in terms of the spectra, and we can study those spectra, but those spectra are far from continuous. In fact, there are only a few discrete lines. And those spectra can be measured by shooting light, by shooting infrared light. Many of them are in the infrared range. By shooting infrared light, then only the wavelengths satisfying certain discrete conditions can be absorbed by the atom. From there on, we can indeed probe the so-called spectrum of a particular species of atom. Okay, and they are not really continuous at all. So this means that the classical physics cannot be used to describe even the a simple atomic model. Okay. So then how do we understand the behavior of electron inside the atom? So first, Bohr, so one of the pioneers of quantum mechanics, proposed this model, and this is the well-known Bohr's hydrogen model. So he proposed a model for the hydrogen atom. Hydrogen atom is very simple. It's one proton and one electron. So in his model, he assumed that electrons do not really go around the nucleus like in the classical fashion. Instead, the behavior of electrons inside the hydrogen atom is discretized. So there are many tracks. So if we still draw these figures, nucleus, and then, so electrons can only exist in those discrete tracks. Okay, so that's the first assumption. And second assumption is if the electron happens to be on one track, then it doesn't give out electromagnetic radiation. Of course, this is against the classical electrodynamics because those tracks are not straight lines, and whenever electrons move around in a circular fashion around the nucleus, they have to give out electromagnetic radiation. So, but Bohr assumed that somehow, without giving the reason why electrons do not give out radiation, he just assumed if electrons fall into those tracks, then the electrons do not give out electromagnetic radiations. Okay, And associated with these individual tracks, there are certain energy level. So the lowest energy level, we call this ground state, E1, and then the next energy level will be E2. That's the first so-called excited state. And then this energy level can keep going. And he found that so the energy level of the nth track is actually pretty simple. It's only inverse proportional to n squared of the E1. Okay. So if we know the ground state energy, E1, this is the ground state. So the so-called ground state comes from the fact that this state has the lowest energy, it's close to the ground. That's why it's called the ground state. So for hydrogen, this E1 is simply minus 13.6 electron volts. Okay. So knowing both of them, E1 and this relation between E and E1, then we can compute the energies of all the different tracks. Then we have E1 here, E1, then E2, and then maybe E3, and then we can keep drawing these energy levels. Okay, so Bohr assumed that if electron stays in those tracks, then the electron doesn't lose any energy. It is a stable structure. If the electron has to move to another state, it can only occupy those discrete states, and so the electron can go from, for instance, from this E3 to E2, and then lose energy. Then those energies are released in the form of light or photon. And there are many transitions among all these different states. So the electron of E2 energy can also hop to E1 and of course release energy. And then electron at E3 can also go all the way to the ground state and release even more energy. Okay. So those energies are in the electron volts range, and so they can be detected. And those are the spectra of the hydrogen. So there are two ways to detect the spectra. First, if the electron in the hydrogen atom is excited, then they can de-excite and go to the lower energy state and release energy. Alternatively, we can also shoot light with the exact energy so that we can reverse this process and excite the electron from the ground state to a higher energy level, or maybe from hydrogen level to an even higher energy level. So the light will be absorbed to the system. So these are two distinct processes. One is the so-called absorption spectra, the other is the emission spectra. So I don't want to go into details, but the main point is the spectra is discrete. Okay. So with these simple assumptions, then we can compare the prediction of this spectra with the experiments, and turned out the comparison is extremely excellent. Okay. So this means that there are some merits in the Bohr's hydrogen model, although he didn't explain why the electron doesn't give out electromagnetic radiations when it is going around the circle. Okay? So that is completely against the classical electrodynamics. So of course that question was later on answered by Schrödinger. So we can directly apply the interaction potential of the interaction between the electron and the proton, which is a Coulombic, then using this potential as the input and solve the Schrödinger equation. Then we can exactly find out the wave function of the electron and also the corresponding energies. So indeed, this En is inverse proportional to n squared. So that will be the topic we're going to talk about in 447. So, but for now, this hand waving explanation is enough. So the key point here is that classical physics cannot be used to explain the stable atomic model. Okay. So because of this work, Bohr won the Nobel Prize in 1922. Okay. So most of the foundational work of quantum mechanics were done at the beginning of the 20th century. So the Nobel Prize started in 1901. So most of the first few Nobel Prize winners in physics made a lot of contributions in quantum mechanics and in atomic and nuclear physics. Okay, so that is the first experimental fact or experimental observation that couldn't be explained by classical physics. Okay, so the second phenomena or experiment that cannot be explained by classical physics is so-called black body radiation. Okay, so black body radiation refers to like any, well, stepping back a little bit. So this is close related to a phenomena called thermal radiation. So thermal radiation refers to any object with non-zero temperature. So it's called thermal radiation with non-zero temperature. So if the object has non-zero temperature, then the particles, atoms, molecules inside this matter are going to move. And when they move, they can collide with each other. So there are accelerations. The molecules and atoms have charges. They have electrons and protons, so they're charged. And when charged particles collide with each other, that creates acceleration. So once again, according to the classical physics, classical electrodynamics, the acceleration of those charged particles are going to generate electromagnetic wave radiation. Okay. And depends on the temperature of the object, then these radiations, the frequency of these radiations can have a very wide distribution. So in our everyday experience, in fact, we do make use of the thermal radiation. So for instance, in winter, so we use the so-called thermal radiator. Right, we use a thermal radiator to heat up the room. Of course, the temperature is not very high, so we cannot directly see those radiations. So those radiations are not in a visible light range. We cannot see them. So, but if the temperature is high enough, then the wavelengths of this thermal radiations are going to shift to the range that we can see with our eyes. So one example would be the stove. Okay? The stove used to cook food. So when I turn on the stove, then beginning in room temperature, so we don't see the radiations. But if the temperature of the stove becomes high enough, then the radiation, or in fact the peak of the radiation falls into the visible light range. So visible light, the wavelength of visible light is is 350 nanometer to 700 nanometer. Okay, so the 350 nanometer will be the blue or violet light. So 700 nanometers will be the red light. Okay, so for stove room temperature thermal radiations, the light so the peak of this radiation will be in the far infrared range. So we cannot see with our eyes, our naked eyes, but of course you can use those thermal goggles and you can see the thermal radiations. I'm sure you've seen that in movies. Okay, so But if the temperature of the stove keeps going higher and higher, then the peak wavelength is going to become shorter and shorter, and eventually enters into this window 350 to 700 nanometers. In fact, it's 7 nanometers. They become shorter than 700 nanometers. Then we begin to see that. Okay? So an interesting temperature, which you might want to remember, is like at what temperature you begin to see the stove become red. So that temperature is so-called the dripper point. Okay, so this is roughly 525 degrees Celsius. Okay. So now in the future, you will know when you turn on your stove, then when you begin to see the reddish color, then means the temperature is about 525 degrees Celsius. Okay. So black body radiation is essentially an idealized version of the thermal radiation. So all kind of matter are going to give out electromagnetic radiations, and at the same time they also absorb radiations. The black body radiation refers to this extreme case. So so that's why it's called black. So it only absorbs radiation, so nothing can be reflected. Okay, so this way it simplifies the problem. Okay, so in order to fully describe the black body radiations, then we also need to know a little bit of classical statistical mechanics, because here we're talking about a macroscopic object. So we need to know the distributions of the velocity inside the materials. So that is not too hard, but it's beyond the scope of this class. So, but what we can say, if we measure the radiation intensity as a function of the frequency, so I as a function for frequency, okay, and what we see is a peak, okay. So, in fact, this cannot be explained by the classical physics. So, in classical physics, so this radiation, in fact, this intensity is proportional to certain power of this frequency, this omega, I think the false power. And this is the so-called Rayleigh-Jeans equation, or Rayleigh-Jeans law. So they using classical electrodynamics, they predict that this radiation intensity will be proportional to some power loss of the frequency. Okay? If you go to higher frequency, the prediction is that there will be stronger and stronger irradiation. So of course, this is not what we see in our day. If this is the case, then every object with finite temperature are going to give stronger and stronger radiation at higher frequency. Like ultraviolet, you can go even higher to X-rays and gamma rays. Okay. So none of us is giving out gamma rays all the time. So something's wrong at higher frequency. Okay. So then, to describe the high frequency, so another physicist, Wayne, his name is Wayne. So Wayne came up with a theory now known as the Wayne displacement law. Okay, so it can be used to describe the high frequency radiations. So essentially solve this disaster at high frequency. But unfortunately, for a very long time, people didn't have a way to reconcile these two ranges. So the radiation generated by this black body cannot be explained in a uniform framework for both low frequency and high frequencies. Okay, so nevertheless, those are important contributions. So win one Nobel Prize. So win one Nobel Prize in 1911. Okay, related to this work, and the simplified version of this Wien displays more is so he predicted the maximum wavelength in this spectrum. So like here, it's inverse proportional to temperature times temperature is equal to a constant. Okay, so in fact this is very useful because so this constant is a universal quantity. So it means if we can measure the spectra and find out the maximum wavelength, then we can easily find out the temperature. Okay. So in fact, this is one way for us to measure temperature of a certain object without contact. For instance, how do we know the temperature of the sun, the temperature of the surface of the sun? So we cannot put a thermocouple on the surface of the sun and measure its temperature. Okay. So, but what we can do is we can measure this radiation spectrum and find out the frequency or the wavelength of the light which is at the peak of this intensity. Then with that, then we can easily find out the temperature. Okay, so that's why Wien won the Nobel Prize in 1911. So really, I also won the Nobel Prize even early. Really won the Nobel Prize in 1904. So of course, not because of this work. A more well-known contribution of Rayleigh is Rayleigh scattering. In fact, the physics shown on this curve, its intensity as a function of frequency in the low frequency range, is indeed the same as the Rayleigh scattering. So the Rayleigh scattering, as you may have heard of before, is responsible for why is the sky blue. Right? If you look at this curve, so the high frequency waves will get scattered more stronger. So that's why like blue lights get scattered more. That's why we see the sky is blue. Okay. So then of course even with this two asymptotic behavior, then it's not satisfactory. So what is the physics behind this black body radiation? How can we come up with a theory that can describe the entire spectrum? So this is where Planck came in. So Planck came in, he came up with a theory. Okay? And the theory, in that theory, he has to assume, so the energy of a wave, in this case, the wave will be electromagnetic wave, is not related to amplitude, but rather to the frequency. Okay, so if you think about any other waves that you have encountered, like classical waves, mechanical wave, sound wave, even electromagnetic wave, so the energy is related to the amplitude of the wave. So the larger the amplitude, of course, the more energy you need. Like at home, if you want to make your speaker louder, then you have to increase amplitude of the sound wave. Right? So, but Planck at the beginning, he didn't believe this is true physics, and that in order to kind of interpolate between this Rayleigh-Jeans law and the Wien displacement law, he has to assume the energy of the electromagnetic wave is proportional to its frequency omega. Then this constant now is known as the Planck constant. In fact, H is called the Planck constant. And we oftentimes use H bar, which is H divided by 2 pi. So that is the reduced Planck constant. It's one of the most important fundamental constants of the universe. Okay, so Planck had to assume the energy of the electromagnetic wave, and later on, this wave is coined with the name photon by Einstein. So only with this assumption, then Planck came up with the analytical form, this intensity as a function of omega. I can write it down here without much explanation. So it's h bar omega to the third power, and then pi square c, the speed of light, c cube, and then 1 over exponential h bar omega over kBt. So kb being the Boltzmann constant minus 1. Okay, and this equation agrees with the experimental observations very well. At short time, it goes back to the Rayleigh-Jeans equation, and at short frequency, at high frequency, and it goes to the Wien displacement law. Okay. So, but Planck himself didn't believe this is true physics, and he didn't understand why the energy is related to frequency, not the amplitude. This is completely against the classical physics. Okay, but it works very well, and there must be a reason. So, well, because of this work, of course, so Planck is considered one of the pioneers of quantum mechanics as well. Okay. So nowadays we take this for granted. It's Planck's formula for black body radiation, and so that's widely accepted, and it can be used for many different things. So if you think about a very big object, the biggest object will be our universe. So according to the Big Bang theory, so the universe started from a singularity point. And at the beginning, the universe is very hot. As the universe is expanding, then the universe is cooled down. Okay? So, but the universe the temperature of the universe is non-zero. So any non-zero object is going to give out electromagnetic radiation. So the universe is it's nothing special. It should also follow the same basic physics. Okay, so then according to both quantum mechanics and also the Big Bang theory, of course nowadays the universe is very cold, but still non-zero. Then the question is, do we have such a black body region from the universe as evidence of the Big Bang? Okay? So that was proposed, before the 70s, I think even early, so 1650s, in 1960s, 1950s. And the physicists have been looking for such a background radiation from the universe. Okay, so and if you think about the times, 1950s, 1970s, so at the time, the electrical engineering had a huge improvement. So while the physicists were searching for this kind of background radiations, and then two electrical engineers, and their name is Penzias and Wilson. So they were engineers at the time at the BioLab. So they were at the BioLab. And they were trying to design new readers and try to minimize the noise. So they found that no matter how careful they are, they won't be able to get rid of one type of one type of electromagnetic wave radiation, and the temperature is roughly 3 Kelvin. The temperature corresponding to the spectra is 3 Kelvin. Okay, so they actually accidentally discovered such a radiation. Now it's called CMB. So it's a cosmic microwave background radiation. Okay, so CMB or CMBR. And this radiation turned out to be roughly 3 Kelvin. Okay. So of course they won Nobel Prize in 1978 because of this important discovery. And recently, not too long ago in 2006, there was another Nobel Prize was given to Smoot and Mather. So they found out that there's some anisotropy in this microwave background radiation. So there are more detailed studies follow up. So even nowadays, it's still ongoing research. Okay. So coming back, the second experiment I want to mention is black body radiation. Okay. So in order to, so this phenomenon cannot be explained by classical physics. In order to explain the black body radiation, we have to assume the energy of the light or electromagnetic wave is proportional frequency. So E is equal to h bar, which is reduce the Planck constant, times omega, which is the angular frequency. Okay. So omega is angular frequency, omega is 2 pi times f. So f is the frequency and omega is the angular frequency. Okay, so that is the second example that cannot be explained by classical physics. So the third example I want to mention is actually close related to the work in our department. It's the photoelectric effect. Photoelectric effect. Okay. So what is the photoelectric effect? So, so it has been observed. If you shoot light onto a piece of metal, okay, and then sometimes the electrons inside the metal can be kicked out. Okay. So then question, how do you understand such a phenomena? So if this light can be described by classical electrodynamics, then it means that if I want to kick out more electrons, then I need to put more energies onto the metal. How do I increase the energy? Then I increase amplitude of the light. Okay. So so that's one way. So you increase amplitude of the light. And second is you can keep even if amplitude is small, then you can keep shining your light to the metal for even longer time. Then with enough time, then the energy can be accumulated enough to kick out the electron. So this would be our understanding according to classical physics. So and then you can run the experiment. You can shoot light to metal and then see when the electrons can be kicked out. So unfortunately, the classical physics once again doesn't work here. Okay. So the observation is that even if we increase the amplitude to be very, very large for the certain wavelength of the light, we'll never be able to see the electron. So we don't get more electrons if we increase the amplitude of light. And we don't get more electrons if we increase the time of the light. Okay, so it turned out that the energy, okay, we can measure the energy of the electron. So E here stands for the energy of the electron as a function of the frequency of the light. It turned out that whether we can get electrons from this photoelectric effect has nothing to do with amplitude or the time of the incident light. Rather, it depends on the frequency of the light, okay, omega. So if for certain material, for certain metal, if we use the light with a frequency more than certain cutoff, omega 0, then the electrons can be kicked out instantaneously. And if we measure the energy of the electron, so the energy electron is linearly proportional to the frequency of the incident light. Okay, but if we use light with the frequency less than its cutoff frequency, omega 0, omega naught, then no matter how long do we irradiate the sample or how much amplitude we apply, then we never see the electron get kicked out. Okay. So in classical physics, so the energy of the light or electromagnetic wave is described by this so-called Poynting vector. Okay. So essentially, it's the energy flux. So that is related to 1 mu naught, it's just a constant. So the electric field across the B field, E cross B. So in that way, so the energy or the energy flux is proportional to the amplitude squared. So now the observation is clearly not following this behavior. So how do we explain that? So once again, to explain this photoelectric effect, we had to use the Planck's assumption. So clearly, the energy of the photon is related to frequency, not the amplitude. Okay. So now we can see this energy is a straight line. So this energy E is equal to h bar times omega minus omega naught. So omega is omega 0, then this is equal to 0. Omega is more than omega 0, then it's a straight line. Okay? It's a very simple. It's a very simple formula. Okay? And this is actually proposed by Einstein. So of course Einstein won Nobel Prize for this. Einstein won the Nobel Prize in 1921. We know Einstein made a lot more contributions, E to mc squared, special relativity, general relativity, Brownian motion, all of those. But actually, no, Einstein won the Nobel Prize because of the simple formula for photoelectric effect. Okay. So in fact, relativity was never given a Nobel Prize. So and to come up with this equation is simple, but they took a genius to give a meaning to this equation. So Einstein took Planck's assumption. Energy of the light is E equal to h bar omega, and he says that this is the physics. So for light with at high frequency, so the energy has nothing to do with amplitude. So E is equal to h bar omega, okay, and he called that a photon. Okay, so this photon sounds like a particle, but it's different from a classical particle. It's a quantum mechanical particle. It has the behavior of both wave and particle. Okay? So this is something we're going to explain next time, the wave-particle duality. Okay? And because of this work, Einstein won the Nobel Prize. So this photoelectric effect is very important for nuclear engineering. In fact, one of the devices we used pretty often made use of this photoelectric effect. It's called photomultiplier. It's an essential component in the scintillator detector. Right? So in scintillator detector, or scintillator or scintillation detector. Detector. Okay. So how does it work? So we know if we want to detect a a photon. It's not that easy. It's just one photon. Then what can we do? So we can shoot these photons to some scintillator. Okay. So then, due to the photoelectric effect, then the electrons can be kicked out. The primary electrons can be kicked out. Then inside this photomultiplier, then you can use one electron to generate two more electrons, and then these two keep generating more and more electrons. Then in the end, you can detect the current. So the photomultiplier make use of the photoelectric effect to multiply the effect of a single electrons to be many of them, which become easier for us to detect. So you will learn a lot of those in the following courses, like NTRE 451. Okay. So stepping back, the take-home message is, in order to explain the photoelectric effect, we also have to accept this concept of photon. Okay. So light at high frequency behaves more like a particle, and the energy is proportional to the frequency. Okay. So the last example I want to mention is the Compton scattering. Okay. So this is observed a little bit later. So in fact, the Nobel Prize was given in 1927, and together with the Compton shared this Nobel Prize with Wilson. Okay, so what is Compton scattering? So Compton scattering is when you shoot photons or light, okay, towards an electron. Okay, so this is electron. So essentially, it describes how a photon gets scattered by electron. So to understand Compton scattering, we need not only to assume the energy of the photon is h bar omega. So that's the energy of the photon. We also have to use a few other assumptions of quantum mechanics, like the momentum of this photon is h bar times k. So k is a wave vector. It's a wave vector, so we treat even one single photon as a wave. So the inverse of this k will give us the wavelength. So 2 pi over lambda is the k. Okay, so so those are this is proposed originally by de Broglie, and this is the main content we're going to talk about next time. So we need to make use of these two assumptions from quantum mechanics. At the same time, we also need to make use of special relativity. Okay. So if we shoot photons to the electron, and then after interaction, say the photon gets scattered, okay, and then the momentum becomes h bar times k prime, and frequency, so p prime becomes h bar times k prime, and e prime becomes h bar times omega prime. Okay, and let's call the scatter angle to be theta. And then the electron will also be kicked by the photon. So electron can also move. So electron will go this way with exciting velocity v. Let's call this angle to be phi. Okay. So so this will only happen when we have high energy photons. When we shoot high energy photons to the electron. So the amount of energy the electron can gain is not small. Then we have to describe the behavior of the electron using special relativity. So in other words, the mass of electron would be equal to So this gamma factor times the rest mass energy of the electron, M naught. So this gamma is this square 1 over square root of 1 minus V squared over C squared. Okay. So then, by making use of these three assumptions, the first one is the Planck's assumption, the energy is h bar omega. And second, we use the Broglie assumption, the momentum is h bar k. And lastly, special relativity. Then we can set up the momentum conservation. So momentum conservation. So that would be so h bar k. So before the collision, the momentum is h bar k. After collision, it's h bar k prime plus the momentum of the electron. Okay, so these are vector equations. Then we can project them in two directions. So the second, so we also have the energy conservation. And before the collision, the energy of the photon is h bar omega plus the rest mass energy of the electron is m naught c squared. Okay. And after the collision, the energy of the photon is bar times omega prime. And then the rest, the energy of the electron becomes mc squared, where m is given above. Okay. So it takes a little bit effort, not much actually. It's algebra, but be a little careful. Then you can find out the difference in the wavelength of the photon. So we shoot a photon with certain wavelength lambda, and then after the scattering, the wavelength becomes lambda prime. So we can measure the difference of the wavelength of the light. Okay. So don't worry, so we're going to do these derivations when we spend more time on the Compton scattering. So later on, that's going to be towards the end of this semester. So but for now, to just let you know, by solving this equation, we can find the difference of the wavelengths. It's very simple. It's only proportional to 1 minus the cosine of the scattering angle theta. Okay, so where this lambda c is equal to 2 pi h bar divided by the rest mass of electron times speed of light. So this is 2.426 times 10 to the minus 12 meter. So this is so-called Compton wavelength. Okay. So now we can do the experiment. We can shoot photons to electrons and detect the difference in the wavelength. So this difference wavelength is oftentimes called the Compton shift. It's the shift in the wavelength of the light, okay, as a function of angle. Then, and we can test whether this Compton shift follows the simple theta dependence, 1 minus cosine theta. And of course, and the experiments agrees with the theories beautifully. And now we accept to describe this phenomenon, we have to use all these three assumptions. So one is the energy. So one is the energy, two is the momentum, and three is the special relativity. Okay. So of course, we're not going to cover special relativity in this class. In the main take-home message is we have to use quantum mechanics to describe this Compton scattering phenomena. Okay. So coming back from the stable atomic model to black body radiation, and then photoelectric effect, and lastly Compton scattering. So all these experiments being designed and carried out at the end of the 19th century and the beginning of 20th century shows that the classical physics is insufficient to describe the subatomic particles. Okay. So there are a few more experiments that we'll carry out during that time and a little bit later, but we don't have time to cover those. So the main experimental observations I want to mention are these four. Okay, and in order to understand this phenomena, we need to introduce new physics. And that new physics at the beginning, um, it's very different from the classical physics. Of course, no one really understands. So for classical physics, oftentimes you can attribute the contributions to one or two persons, like Newton's equation for classical mechanics, or Maxwell for the Maxwell's equations in classical electrodynamics, or Boltzmann for classical statistical mechanics. For quantum mechanics, as you can see here, a lot of really smart people made important contributions. So from the early days, Bohr and Planck, Einstein, Compton, and of course many more later on, Schrödinger, Dirac. So those were the pioneers who worked very hard on quantum mechanics at the beginning of the 20th century. And they set out the foundations for us to quantitatively describe the phenomena in the atomic and the nuclear scale. Okay, so that's the lecture on the historical background and experiments of quantum mechanics.